Welcome back, Math 82 folks. Today we are going to learn about a method that will allow us to solve a more general class of second-order ordinary differential equations. That method is the variation of parameters method. So far in this course, we have learned to solve initial value problems that look like this. You notice that these are constant coefficient and homogeneous. Note that this is the ODE in its normal form, which means, of course, that the highest derivative term has a 1 in front of it. Now, generalizing from this type of constant coefficient homogeneous second-order ordinary differential equation, we are going to implement two major changes. We are now going to look at an initial value problem that has time-dependent coefficients, which we will call functions p1 of t and p2 of t. And the ODE is no longer homogeneous because there is going to be a non-zero forcing term, which we are calling f of t. Now, this f of t, it could be a function of time or it could just be a constant. It's important to note that the techniques that we have learned so far for dealing with the constant coefficient second-order ordinary differential equation that is homogeneous no longer apply. We cannot use the characteristic equation technique directly on our inhomogeneous or driven ODE. So what can we do? What is the idea behind the variation of parameters method? We do have to start with a fairly important supposition, and that supposition is that we already know how to solve the associated homogeneous ODE. That is, we know how to find the general solution or the basis of the solution space to the associated homogeneous ODE. In particular, the general solution to the associated homogeneous ODE will have the form C1y1 plus C2y2, where y1 and y2 are the basis of the homogeneous solution space. This is why we say that y1 and y2 must be two linearly independent solutions to the homogeneous ordinary differential equation. Again, let me emphasize here that the solution to the homogeneous differential equation must be known before we can apply the variation of parameters method. Now we can move on to figuring out how to solve the associated forced version of the ordinary differential equation given here. How do we do that? We are going to assume that the solution has a form similar to that of the associated homogeneous ODE, except that we are going to allow the coefficients in front of our basis functions to now be functions of time. Now here's our question. What can we say about those basis functions if they are solutions to the homogeneous ODE? Here is a key fact that we are going to have to keep in mind. We know that since they are solutions to the homogeneous ODE, when you plug in either one of them, you will get a 0 on the right-hand side. We are going to come back to using this a bit later. Now again, let's come back to this idea of assuming that this ODE has solutions of the form u1, y1 plus u2, y2, where u1 and y2 are now functions that we have to find. How shall we go about figuring out what that mysterious u1 and u2 are going to be? Let's first differentiate our general solution. Now remember, because we are differentiating products of functions, we do have to use the product rule, which ends up giving us a u1 prime y1 plus u1 y1 prime plus a u2 prime y2 plus a u2 y2 prime. We can see that this might start getting a little bit hairy if we differentiate a second time. So before we take another derivative, let's do something that is going to help us out a lot. And what we are going to do is impose this constraint that we want u1 prime y1 plus u2 prime y2 to equal 0. Why are we allowed to impose that constraint? Well, we can do anything we want because we made up u1 and u2. And so we are going to make u1 and u2 help us with the form that we give them. What does this now give us? We have now created a simplified form for the first derivative y prime, which is u1 y1 prime plus u2 y2 prime. On the next page, we have moved that equation to the top here. Let's differentiate a second time to see what we get. Now we have y double prime in terms of u1 and u2 and their first derivatives, and in terms of y1 and y2 and their first and second derivatives. Again, let's keep straight what is so far known and so far unknown. We know y1 and y2, and we are trying to find u1 and u2. Now let's take what we have found for our solution y prime from pink equation happy face, and for our solution y double prime from blue equation star, and plug it in to the original non-constant coefficient inhomogeneous ODE that we started with. This first part is our y double prime added to P1 plus y prime added to P2 plus y. That whole thing equals our inhomogeneous right-hand side, F. At this point, we are going to rearrange some of these terms to see what we can simplify. This particular rearrangement is quite useful for us. Why? Do you recognize what we can do with these? Remember that since y1 and y2 are basis functions of the homogeneous solution space, then when you plug those into the ODE, you get 0. This simplifies our process greatly, because now this entire thing has collapsed into the following: u1 prime y1 prime plus u2 prime y2 prime equals our function f. What has this done for us? This has actually given us two unknowns and two equations. Our two unknowns again are the u1 and the u2. This first equation comes from our imposed constraint that we wanted u1 prime y1 plus u2 prime y2 equals 0. The second equation comes from what we just calculated. It is, in fact, the result of rewriting our forced ODE. What is it that is useful about this form? Notice again, keeping straight what is known and what is unknown, it's the u1 and u2 that we're trying to find. And in fact, we've got two linear equations for the derivatives of u1 and u2. Let's rewrite these equations in matrix form. Putting our unknowns u1 prime and u2 prime into the unknown vector, we have a matrix of known values made up of y1 and y2 and its derivatives. We also know the right-hand side f. Now, when will this system have a unique solution vector? Remember from linear algebra that when you're looking at a system AX equals B, it has a unique solution if and only if the matrix A is invertible. That means that the determinant of that matrix A has to be non-zero. What is our matrix A in this case? In this case, our matrix A is this matrix with y1 and y2 in the top row and y1 prime, y2 prime in the bottom row. So this system will have a unique solution if and only if the determinant of that matrix A is non-zero. This is a crucial point. We want that determinant to be non-zero. That determinant is so important, it's actually been given a special name. It's called the Wronskian of the two functions y1 and y2. And it is defined to be the determinant of the matrix whose top row is y1 and y2 and whose bottom row is y1 prime and y2 prime. Now, coming back to our system of equations that we want to solve, how do we do that? If we assume that the matrix A is indeed invertible, let's multiply both sides of that equation by the inverse of A. In this case, you end up isolating your unknown vector u1 prime, u2 prime. And you notice that in this solution, what shows up is the Wronskian and all known values y1 and y2, their derivatives, and the right-hand side f. Here's a brief aside. Remember that the inverse of a 2 by 2 matrix, A, B, C, D, is given by 1 over the determinant of that matrix times D minus B minus C, A. And that is what we used to create the inverse and find the solution. And now we're done, because what we have shown is that we have a form for the derivative of the unknown u1 prime and the unknown u2 prime in terms of things that we do know, which are y2 f and the Wronskian and y1 f and the Wronskian. So there's only one important step left, which is to solve these very simple first order ODEs by integrating. What we have created here is an actual formula for these previously unknown functions u1 and u2 so that when we go back and plug them into our solution form, we have a general solution for the non-constant coefficient in homogeneous ODE. Let's summarize what we just learned. Remember that the Wronskian of two functions, y1 and y2, is this function that is the determinant of the special matrix that has y1, y2 in the top row and y1 prime, y2 prime in the bottom row. The Wronskian itself is considered a function of y1, y2, and its derivatives. And now what about finding the solution to the general second order linear forced ODE of this form? Remember, putting it into normal form is crucial. We first solve the homogeneous unforced version of the DE and obtain its two linearly independent solutions, y1 and y2. Then we actually have a formula for the general solution of the forced ODE, which is given by the following. This first integral, remember, is u1, y1. And the second integral is u2, y2. Now just remember that if you do not write your equation in normal form, you will misidentify the forcing function, and that can cause problems when looking for a solution. Some important things to keep in mind. You'll want to make sure you know how to identify when a linear ODE is forced. Make sure you understand the main idea behind the variation of parameters method. Remember, the big picture is that we are taking a combination of the basis functions of the solution space of the associated homogeneous DE, combining them with functions as opposed to constants, and then searching for what those functions, u1 and u2, are by taking derivatives and making some simplifying assumptions. Be aware of the Wronskian and how to find it and how to make use of it. And finally, make sure that you can apply the variation of parameters method to a linear forced second order ODE by both using the formula and by going through the derivation from scratch. Okay, that is how we use variation of parameters to solve a second order forced ordinary differential equation. We are going to practice with examples in class. We'll see you then. Take care.